Hey guys, welcome back to part 4 of the DIY flight controller series. Now today's video is going to be a fairly quick one, and I'm going to just give you a broad overview as to what our system looks like as a whole, and show you roughly how our controller is going to interact with our quadcopter in order to keep things stable. So let's just dive straight into it. How does our quadcopter remain perfectly level at all times, even in the presence of external disturbances such as a gust of wind? Well, in order to answer that, I'm going to illustrate things with the help of a block diagram. Now, block diagrams are a great tool in controls engineering in order to visualize your system. So let's just start over here. All the way on the left, I have my desired output. Now, this is my desired position, angular position of the quadcopter. All the way on the right here, I have the actual measured output, and this is the actual measured angular position of the quadcopter. Now, at the end of the day, our goal is to make sure that the actual measured output is as close as possible to our desired output. So how do we do that? Well, it helps to think of things in terms of some sort of error term, and we can generate this error by looking at the difference between the desired and the measured output. So our error is just yd minus y, and we can draw this in our block diagram like this. So now we have this big gap over here. How do we then relate this error term to our actual output? How do we use this in order to generate the quadcopter's motion? Well, let's work from the output backwards. If you remember in the previous video, we developed a state space model of the quadcopter that relates some input u to our output y. So that's a perfect place to put the state space block. We'll put our quadcopter right here. Now the inputs u, if you recall, are the angular accelerations about the x, y, and z axes, and the outputs y are the angular positions. So now we have this smaller gap here, where we need to somehow relate the error term to the input signals that go into the quadcopter. And this is the job of the controller. The controller does exactly that. It takes the error signals as an input, and the output of the controller is the input of the quadcopter. It somehow figures out how to generate the appropriate signals to the quadcopter in order to bring that error back to zero. Now, a great place to start for this controller is by using a PID controller. If you've ever flown quadcopters, the term PID should be fairly familiar to you. Now, I don't want to go into the maths behind how a PID controller works in this particular video, because the goal of this video is to give you a big picture overview. But a PID controller is an excellent controller because it simply just works, and it's fairly easy to implement and fairly easy to understand. So this is our system as a whole. We have essentially a controller that takes the error term and generates an input signal for the quadcopter, and then we measure the quadcopter's actual output, compare it against the desired output that generates the error, and we close the loop. So I hope that going through designing this block diagram with you gives you a better understanding of what it is we're actually trying to do. We're trying to design this controller that stabilizes our quadcopter by looking at this error term. And if you can understand this very broadly, you should be completely fine going forward, because at the end of the day, this is the essence of what we are doing. We are designing this controller right here. In the previous two videos, we actually figured out how to mathematically represent this model of the quadcopter, which is important in order to design the controller. But it's not what we're actually trying to design at the end of the day. That's just the quadcopter. We're trying to design the controller. So that's pretty much it for this video. I really just wanted to give you this picture of what our system looks like as a whole. Now, in the next few videos, we're going to segue into something more practical and exciting. We're going to be building up this quadcopter test platform, which will actually run our flight control code when we write it. And I'm going to show you guys, first of all, how to interface things like the motors, the receiver with the S-bus, and the gyro and accelerometer, because that's going to be fairly important to us. So I hope that keeps you guys interested, and I hope that you got something out of this video, and I'll catch you guys next time.